Good morning, ma'am. We are presenting a topic of elliptical cryptography. My group members are Shreya Chaugule, Omkar Pawar, and myself Sohani Patil. First of all, we got the information of elliptical cryptography from the abstract paper. That is, we got introduction part, background information of the elliptical cryptography, design and implementation of RNS. That is, RNS is the received number system. We got the key points: RNS is arithmetic, that is received number system, elliptical cryptography arithmetic. We got the last 2 points, that is implementation results overview and the area analysis of point multiplication latency. Basically, we got the information about elliptical cryptography in the introduction part. I explained the introduction part in very small and the understandable language. That is, first of all, we think about the today's technology, where sheer number of Internet of Things application use hardware security modules. For what purpose? They are using the hardware security modules for secure communication and other purposes. So basically, the widely used algorithms in that security models, which is used for secure communication, these security models are digital signature, key agreement, which is based upon the elliptical cryptography. A core operation which is used in ECC is the point multiplication. That the information we got in the abstract paper. So basically, considerable research has been conducted in the design of fast elliptical arithmetic on finite fields like the as early I mentioned the received number system, that is RNS. In this paper, we propose an RNS-based ECC core hardware for the two families for the elliptic curves that are short, Weierstrass and twisted Edwards curves. We implemented different ECC point multiplication algorithms on this platform, that is a FPGA platform. The test results confirm that the performance of our fully RNS is. Move forward the background information of elliptical cryptography, RNS based ECC hardware, in which we got the points, that is HSMS ECC, core operation of ECC, challenges, RNS contribution. What include in that? That is secure devices for encryption, key generation, digital signatures. ECC means efficient public key algorithm that is very crucial for IoT. In core operation, we got the three points, that is point addition ECPA, point doubling ECPD, point tripling ECPT. We got the challenge, that is fast ECC point multiplication for high throughput application. The application which has a high throughput, we've got them for the high or fast ECC multiplication. So basically, in RNS, we use modular arithmetic for what purpose? The parallel processing, and it increase or improves cryptographic speed. So as earlier I mentioned the two families of elliptic curve, that is short Weierstrass elliptic curve, and in the main purpose standard curve is there, and the sub part of that is Koblitz curve and twisted Edwards curve. In earlier in introduction part, I only mentioned the two parts, that is a short Weierstrass elliptic curve and twisted Edwards curves. So basically, what happened in short Weierstrass elliptic curve? There are equations. The field of a short Weierstrass elliptic curve parameters, set of points, discriminant condition. In indiscriminate condition, we are now having the multiple tangent lines. Basically, there are two parameters A and B, which belongs to F. Then the equation we got for the short Weierstrass elliptic curve, y square is equal to x cube plus ax plus b. So while moving toward the twisted Edwards curves, which is having one parameter which is equal to -1 mod p. So here we got the information of equation also, which is E is equal to ax square plus y square is equal to 1 plus.
Myself Shreya Chaugule. I am going to explain design and implementation of residual number system arithmetic operations used in elliptical curve cryptography. This concept is about how to perform arithmetic operations in residual number system for elliptical curve cryptography on 256-bit prime field. Using a modulicity that supports a 528-bit range, RNS makes addition, subtraction, and multiplication more efficient by avoiding carrying propagation between channels. For addition and subtraction, it uses specialized hardware with carry save address and multiplexer to quickly compute the results. To avoid negative results in subtraction, a multiplication of prime number is added. Multiplication involves simple multipliers and efficient reduction techniques. Overall, these methods enhance the speed and area efficiency of ECC operations using RNS. This concept is all about RNS builder reduction in ECC. Our RNS-based ECC design features a modular reduction unit that leverages and improves the sum of reduction, which are available in two architectures, SOR1M with one RNS multiplier and SOR2M with two parallel RNS multiplier. This setup efficiently handles addition, subtraction, and multiplication to reducing using a 520-bit dynamic range, which minimizes the number of required modular operations and increases computation speed. The ECC point multiplication is optimized for some curves benefiting from parallel reduction with two SOR units to reduce latency. The hardware configuration includes shared control and arithmetic resources, with the state machine managing data flow and point multiplication, ensuring efficient and accurate electrical curve operations. Here we discuss the efficient arithmetic operation in ECC using RNS. For point doubling, we used a method requiring only 6 modular reductions with parallel processing, enhancing speed and performance. Point addition involves 15 modular reductions, significantly fewer than traditional methods, and uses parallel SOR processing to reduce latency. Tripling essential for scalar multiplication in cryptography needs just 10 modular reductions, streamlining the process for faster computation. This optimized technique significantly improved computational speed and efficiency, crucial for secure and scalable ECC implementation.
Myself Omkar Pawar. I am explaining ECC. The operation doubling and addition reduce the modular reductions, tripling 11 modular reduction and 8 logic levels. Conclusion: RNS improves ECC performance on FPGAs, significant latency reductions with SOR units, efficient and secure hardware implementations. Next is implementation results overview. First is platform and second is performance testing. In performance testing, tested with 1000 random 255 to 256 bit numbers for point multiplication. Average latency measured for each algorithm. Latency measurement used the SOR 1 meter and SOR 2 min units. Clock speeds are 125 MHz to 181.8 MHz. The results are latency and logic area compared for both units. Efficiency measured using area into time parameter. This slide we can see point multiplication, latency and area analysis. The first block is for latency and second block is for area.